Test son, tu m'entends? Dario, Hilton tells me that in 5 minutes they should be in the room for the defense.
Okay, no problem.
Yes.
Julien, if there is Hilton, I would like to say hello to him.
Yeah, he showed up, but he's gone again. But if he enters the room, I'll tell him.
Okay, okay. Yeah, later on there will be time.
Ethan, Dario, il veut te dire bonjour. Pardon? Dario veut te dire bonjour. Hey Dario, do you see me?
Hello, yes, I can hear you.
Are you there, huh? Catch up in a sec. Thanks for being there. Okay, so Dario, the jury has arrived, and I guess we will start soon.
Bonjour, everyone. I have the honor to be the president today. I suggest that we, sorry, I'm Gilles Tessier from Sorbonne University. I suggest that we start right away.
Okay. You ready, Dario?
Yes, yes, you can start.
Dear member of the jury, dear family, dear friends, today I'm going to be defending my PhD, which is entitled Superresolution Imaging in Coherent Raman Scattering for Biological Tissues. I did my work at the Laboratoire Casser Brussels under the supervision of Sylvain Gigant and Hilton Barbosa de Aker. This is the outline for this talk, but first, let's put some context in this PhD. So basically, the outline of my talk is the goal of my talks is to give one answer to this very broad question, which is how to image at high resolution deep inside biological tissue in a label-free manner. And this is the whole objective of this PhD, is to give one possible answer to this question. Now, let's have a closer look at the title of the PhD. In this title, you can see imaging. Imaging, in our case, stands for the use of a microscope, which enables us to unveil what the naked eye cannot see. But what are we using this microscope for? We're using this microscope to have a look at biological tissues. These biological tissues are about 1 micrometer in size. And in this PhD, we had a look at living cells and axons from the neuron. These two kinds of cells are important to understand the biological structures and some biological mechanism, and can lead to a better understanding of biological diseases. But sometimes the imaging that we are making with a regular microscope don't have a high resolution enough. That's why we have here super resolution in this title. And I'm going to explain later what is a super resolution technique, but the key point is that when we don't use a super resolution technique, we can get, for example, this kind of image. And when we go for a super resolution technique, we are able to unveil the proper structure, for example, here, a granular structure. Finally, in this title, there is coherent Raman scattering. And this is the contrast mechanism that we're going to use to produce the images. And I'm going to explain to you what it is, but the main idea is that it's generated by every single molecule. So in the first part of this talk, I will introduce you to 3 main features. I will introduce you to the microscopy for biology. Then we're going to talk about the Raman scattering and the origin of this phenomenon, what it's useful for, the pros and cons. And finally, we're going to choose one super resolution method. But first, let's start with what can limit an optical system. Let's talk about the resolution limit, which is a fundamental limit called AB limit. This limit depends on the wavelength that is used to illuminate an object, and it's also dependent on the aperture of the optical instrument. For example, let's take the eye, the human eye. We are able to see an object which are as small as 100 micrometer, which is more or less the human hair size. But if you use exactly the same wavelength, so basically visible wavelengths, and you use an optical microscope, since the aperture of an optical microscope is higher, we can see even down to the cell level and access to the cell constituents. This is one fundamental limit for imaging. But there's another one. When we're imaging in biological tissues, there's inhomogeneities in your biological sample. This biological sample can be modeled by an heterogeneous medium like that. Heterogeneous medium are where scattering happens. And a second limit to the image quality that are acquired with the microscope is the elastic scattering. Elastic scattering means that the incoming wavelength and the scattered wavelength is the same, but when an incident beam meets with a scatterer, the light is deviated from its originating direction. Depending on the size, it can be mostly forward or be isotropic scattering. So now let's take an example with an homogeneous medium. If we take some lights and focus it after an homogeneous medium, we get a nice airy pattern, which is why images are limited by the AB limit. Now, if we have a biological sample, so we have a scattering medium, there are a lot of heterogeneities in this medium. So now let's have a look at what will happen for one beam path. Let's take this one. As you can see, it's meeting here a scatter. And instead of going straight, it gets deviated from its originating direction. It meets here a second scatterer. So it does exactly the same, and so on and so forth, until the end of this homogeneous medium. Now we're doing the same for all the beam paths. And this is what we get, and we get a completely distorted wavefront, which will result in a so-called speckle pattern with the same wavelength. But scattering is not always bad for imaging. Indeed, there's another kind of scattering which is called inelastic scattering. Inelastic scattering because the wavelengths, the incident wavelengths and the scattered wavelengths are different, as long as also the direction of the incoming beam is different. And this is a nice phenomenon because with the new wavelengths, we're able to relate to the polystyrene, for example, molecule here. Indeed, we can measure a spectrum of this emission and understand the vibrational structure of these polystyrene bits. This is called spontaneous Raman scattering, and it was discovered in 1928 by Raman and Krishna. But how did they discover that? They used a mercury lamp that they focused through air and observed at the mercury lamp spectrum. Then they replaced air by liquid benzene. And they observed that there was a new spectral band, new spectral bands appearing here, which are the sign for spontaneous Raman emission. But what is happening at the microscopic level? At the microscopic level, there's an incident beam going onto some molecules, a scatterer, and this molecule can vibrate in any of the vibrational modes, which are these new wavelengths. So this interaction between the incoming beam and the vibrational modes of the scatterer is the phenomenon producing this spectrum, this Raman spectrum, and giving us information on the vibrational structure of the molecules. But what is happening at the energy level diagram? For elastic scattering, which is called also Rayleigh scattering, the molecule is taken from the ground state, it goes to a virtual state, and de-excites back to the ground state. This phenomenon is at the origin of the color of the sky and the color of the clouds. And on the other side, there's the inelastic scattering. In the inelastic scattering case, the molecule is taken from the ground state, goes to a virtual state, but it de-excites in vibrational states. This vibrational state and the observation of these wavelengths finally give us the information about the vibrational structure of these molecules. But here I talked only about spontaneous Raman. Spontaneous Raman is not very efficient, and the light can be scattered in any direction, making it sometimes difficult to observe. When we're using coherent Raman scattering, which uses two beams here, in fact, we are taking the molecule from the ground state, we're going to a vibrational virtual state, but the de-excitation is stimulated, meaning that this vibrational band is favored against the others. And also, the emission of the scatterer is directive, meaning that it can be collected more easily in one direction. But what is happening now at the microscopic level? As you remember, all the vibrational states are excited when you have only one incoming wavelength, one incoming beam, and you're doing spontaneous Raman. When we're using coherent Raman, we are only selecting, let's say, one vibrational mode, which means that we are taking only one part of the spectrum, for example. if we simplify. The difference between the question can be, how do we address this mode and not the one next to it? And this is set by the difference in energy and so in wavelengths of the two incoming beams. But now one could ask, why are we using Raman scattering and not fluorescence? Because fluorescence is what is the mostly used currently in biology, and it's very efficient signal-wise. On the other side, for biological tissues, it's not that simple. Indeed, for fluorescence, the mechanism is the following. You take the molecule from the ground state, and there's an absorption of one photon in the electronic state. Then there's non-radiative de-excitation and a spontaneous emission. But to have fluorescence, a biological sample need to have the correct energy difference here to generate fluorescence. Since most of the biological tissues don't have the correct energy gap, we need to inject labels, engineered labels. And sometimes we can face some issues like the fluorophore availability or cell viability. On the other side, for Raman scattering, you don't need these labels because it's label-free. And in the coherent case, it can also be chemically selective. But it's a very weak signal and very difficult to observe. This is a very important drawback that we're going to consider when choosing the super resolution technique that we're going to use. So keep in mind the pros and cons of the Raman scattering. Now here, as you remember, this is the AB resolution limit. When we mean super resolution limit, the super resolution technique is a technique that can go beyond this fundamental limit. But this limit is still holding true. It's just that super resolution technique are using tricks to get around it. And here are the three main techniques in the far field for super resolution. You have localization, stimulated emission depletion, and structured illumination microscopy. In localization, the two most widely used technique are Palm and Storm, and here you can see a related example where you see blinking markers here, from which we find the center and reconstruct these nice images. The only issue is that, for example, we need blinking markers, and in a Raman, we want to stay label-free. Then there's the STED-like approach. You need two beams in the STED-like approach. One is an airy pattern, and the other one is a donut-shaped beam, which are overlapped. The objective of this donut-shaped beam is to deplete the beam, this green beam, to make it a smaller excitation PSF. The only issue is that this reduction in the excitation spot is proportional to the intensity of this donut-shaped beam. So in the case of fluorescence, it's perfectly working on biological sample, but you're still limited in the diffraction limit by the energy that your medium can hold, can sustain with this donut-shaped beam. That's why in Raman scattering case, it was only shown in literature on glass and diamond, which are very robust materials. And this is all because of the weak efficiency of Raman scattering. So finally, we decided to work with a structured illumination. I will tell you more about the principle in the later slides. But in the literature, it was shown that for spontaneous Raman and structured illumination were combined here to acquire these two images. But as I told you, spontaneous Raman is not as efficient as the coherent Raman. And these two images took 2 hours to obtain. So in this PhD, we decided to go for coherent Raman scattering to speed up the image acquisition process. To conclude this first part, I introduced the microscopy in the principle of microscopy in biology. I told you about the labor-free and chemical selectivity of Raman scattering. And finally, I explained why we chose structured illumination as a super resolution technique. Now, let's have a look at the outline for this talk. First, I will introduce you to the blind F3 technique, which is the technique that was developed during this PhD. I will tell you about the principle, I will show you the experimental results, and finally, we'll have a look at a key feature, which is called sectioning. In a later part, we're gonna have a look at how we can try to improve even further the spatial resolution. Let's go back to the structured illumination principle. Here on the left, you have an object in the spatial domain. Here is the spatial frequency domain, and let's imagine that these triangles are the spatial frequencies from that object. When we are imaging it, we are limited by the Hab diffraction limit. So we are not accessing all the spatial frequencies. And the green area here are all the spatial frequency which are reachable with structured illumination. So we can wonder, how do we can we recover these spatial frequencies? In fact, by changing the illumination pattern from homogeneous to structured, so here a sinusoidal pattern, we are moving and exploring the spatial frequency space, which is accessible with the Fourier transform. But as you can see, with only one image, we are accessing new spatial frequencies, but we're missing some, and we are even missing some that we had before. So we need more images. And we need to try another structured illumination and so on and so forth. And we finally explore the whole area here of the spatial frequency domain. In practice, there's a need for 4 to 9 images to reconstruct properly an image. And these 4 to 9 images are used as an input in a reconstruction algorithm, which then combines all the spatial frequencies in one single image, as you can see here. Now, let's stop a few minutes on the structured illumination reconstruction algorithm. When we have an homogeneous medium, we are able to obtain the structured illumination on the object, which are perfectly the one we wanted, which means, and the reconstruction algorithm is using it as an assumption. So when we are in this case, the image can be reconstructed nicely. In the case of an heterogeneous medium, there can be the appearance of a speckle pattern on top of the structured illumination, or the structured illumination can be completely distorted. So now the assumption will not hold true anymore, which will result in a reconstruction which contains artifacts. But there's another kind of algorithm which is called blind structured illumination. In this case, instead of having this assumption that the object is illuminated with this pattern, we are changing the assumptions of it. In fact, we are going to assume that the illumination pattern is only limited by diffraction, and we require the sample to be homogeneously illuminated. So when we do that, we can replace the structured illumination with speckle patterns. The trade-off, the price to pay, is that we need a lot more images. in our case, in this PhD, we at least need 100 to 700 images instead of 4 to 9. But with these assumptions fulfilled, we can, with the blind sim algorithm, reconstruct the illumination patterns and reconstruct a superresolved object. So in the blind sim configuration, we can replace the illumination pattern with the speckle. We use the stack of images in the reconstruction algorithm, but it works more or less with the same principle. Now I'm going to sum up the blind sim principle. Indeed, when we chose this super resolution algorithm, we chose it so that the spatial resolution was not dependent on intensity. With the use of blind structured illumination, we are compatible with the biological tissues. Also, we didn't need in the principle to have labels so that the super resolution technique would work. But now we can wonder, how do we combine this technique with Raman scattering? And this was the technique that we developed during this PhD. We called it blind A3, which stands for single pixel stimulated Raman scattering. Since we are using stimulated Raman scattering, there are two incoming beams, the pump beam and the Stokes beam. Now, during this PhD, we always compared conventional SRS with the blind S3. Let's imagine that we have a 1 micrometer diameter polystyrene beads. In the conventional SRS case, the two beams are spatially overlapped and temporally overlapped. And then this these beams are scanned over the object and require one image, pixel by pixel. In the blind A3 case, there's a static speckle illuminating the sample, then another one, and another one, and another one to make 100 or 700 images that then are fed to a blind reconstruction algorithm, which result, for example, in these experimental images. But as you can notice, here on the outside part of this image, the reconstruction is working a bit worse than the conventional SRS. This is induced by the speckle envelope of the average speckle envelope of the illuminations, which is Gaussian. But to make sure everything was working as intended, we run several experiments. We used different polystyrene beads of different diameter. And we reconstruct the images and measure the beads in close contact. And the distance was corresponding to the expected nominal diameter, as you can see here with this nice x equal y curve. Now, let's have a look at the more realistic setup. Here, you have the conventional SRS, which consists of two overlapping beams, which are scanned with two galvanometric mirrors and focused with a microscope objective. On the other side, here you have the blind A3, where one of the two beams is doing exactly the same as in the conventional case, which means that it's scanned in the sample plane. The other beam is illuminating an SLM, a spatial light modulator, which is printing a random phase mask to generate a speckle pattern. Now let's have a look at the image formation, image formation mechanism that and the signal that we are collecting. Since we are using stimulated Raman scattering, our detection is sensitive to the imaginary part of the nonlinear susceptibility. We have a static speckle pattern for the pump intensity, so we are multiplying it by the term. there's one beam which is scanning the whole sample, and this is why we have a convolution here of the Stokes beam. And it results in this image formation equation, which is similar to the blind SIM, regular blind SIM family of problems. So we managed to combine the Raman scattering contrast mechanism with the family of blind SIM problems. So we can use the same reconstruction algorithms. Now that we have a setup that is working as intended, we're gonna try more challenging samples. Here, we estimated the limit of diffraction, theoretical limit of the SRS to 256 nanometer. So we decided to run the experiment with smaller bits. Here, 239 nanometers. And here is the result. On the left, you have the conventional SRS, where you can see that we are not able to unveil the bit structure. While in the blind F3, we are able to distinguish between the bit structure. And it's further confirmed by the line profiles here, where you can see a nice improvement in the resolution. So now that we have, we managed to have super resolution on polystyrene bits, we decided to go for biological samples. But first, we tried with HeLa cells because they are low scattering biological samples. Here is an overview of this cell that we acquired with conventional SRS. And let's have a closer look at this region here. As you can see here, there's a resolution improvement between the conventional and the blind SIM, which is blind F3, which is further confirmed by the line profile here. But more interestingly, here in this other close-up, we are looking. So we are looking at the lipidic content of these HeLa cells, which are spherical. These lipid droplets. And as we can see here, it seems that it's not completely, it's not nicely spherical, and we can wonder, is it the true structure? And as you can see here with the blind S3, we are starting to distinguish between two spherical components, as it's further confirmed by the line profile here, where you can see a nice bump into the line profile, while it's still it's a large bump in the conventional SRS. So then we decided to go for more complicated biological samples, which are here brain slices, and more precisely cerebellum of a mouse. These samples are highly scattering, as you can see within this low magnification image of the cell. It's completely white, which is a sign for the scattering of the sample. And we had a look at this small red dashed rectangle. Here is an overview of this region. And we had a closer look at these dashed white lines. We observed these two images. Here, the conventional SRS, where we can see two rings, two axons cut in the sagittal plane, where we hardly see the distinction between these two rings. In the blind SIM case, we are able to distinguish slightly more the difference between the two rings, which is further confirmed by the line profile here, where we can see that there's a large bump for the conventional SRS, while there are two dips for the blind F3. So we saw that the blind F3 was compatible with the biological tissues. In the rest of this talk, I'm going to talk now about the sectioning ability. But what is sectioning? First, sectioning is a very important feature for biologists. and we need to we will have a look if it's built in the blind A3 principle. But let's go back to what is sectioning. Sectioning is in fact the ability to reject the signal from above and below the focus. Here you have a one photon fluorescence sensitive medium where we can see that the signal can be collected from everywhere above and below the focus, which means that for this linear phenomenon, there is no excitation sectioning. But when we go for a higher nonlinearity, for example, the second two photon fluorescence, we can see that there is no signal coming from above and below the focus anymore, meaning that the technique has an excitation section. And now we can wonder, does blind A3 have sectioning? And we can wonder that because in general, for blind SIM techniques, we are illuminating the sample with a wide field configuration, which means that we don't have sectioning. In our case, we have two focusing beams, one which is tightly focused and the other one which is a bit more loosely focused. So we can wonder, do we have sectioning with this slightly different configuration from the blind SIM, regular blind SIM? That's why we run this experiment. We set the two beams to match the Raman resonance of a thin film of oil. This thin film of oil, we scanned it in the Z direction and collected the signal afterward. And here is the result. When we are at the focus, we have a lot of signal. And when we are above or below the focus, the signal is quickly dropping, which is a sign for a sectioning. So we demonstrated that we have sectioning built in the blind A3 methodology. So I demonstrated in this part of the talk, I explained the blind SIM principle in this part of the talk. I showed you experimental results on biological samples. And finally, I demonstrated that the blind A3 has sectioning abilities. And now we can start to wonder, is it possible to improve even further the spatial resolution with the same principle, the blind A3 principle? Here are the forward model for the combination of blind SIM with simulated Raman scattering and coherent anti-Stokes Raman scattering cars. As you can see here, the main difference is the intensity of the pump beam, which is linear in the SOS case and quadratically dependent in the cars case, which means that the PSF for the cars will be smaller for the pump, which results in an overall smaller PSF. But let's not forget that we are not using focused beam, but speckles. And these two speckles are very different, and we are going to explain more in details a bit later. But the main objective to use cars is to go for nonlinear structured illumination to improve the resolution. And the first problem that we will face is the fact that this speckle is pretty, let's say, dark. Indeed, when we look at the probability density function, so the intensity statistics of these images, we can see that for the Rayleigh, so this one, the standard speckle, the probability to have a higher intensity compared to the mean in the case where the speckle is squared is much higher. But also, the probability to have a low intensity compared to the mean is higher as well. In fact, this image has a contrast which is much higher than 1. And this will result in the fact that there's few very intense bits will in fact increase the sparsity of this speckle, which could be an issue for blind sim, since we need to fulfill the requirement of the homogeneous illumination of the sample. But so that we can wonder how are we going to cope with the blind sim and this increase in sparsity. So we run some simulation. We used the assignment star object as an illuminated object, and we illuminated it with different speckle PDF, speckle probability density function, and a reduced number of images, let's say 5. Then we increased the number of speckle illumination to 10, and so on and so forth. So for these two different probability density function, Rayleigh and Rayleigh squared, we see that the reconstruction is faster for the Rayleigh PDF. While even with the up to almost 200 images, the Rayleigh square is barely able to reconstruct the image. So we can wonder, well, what can we do? And one idea could be that the Rayleigh squared, instead of having this speckle PDF, could have a perfectly matching Rayleigh PDF. So we would like our Rayleigh square to match the Rayleigh PDF. And for that, we would need a linear speckle, which has the following statistic. And this is what is called a Subrayleigh speckle, which means that its contrast is below 1. In the literature, there's an example of such a technique. In this paper, they are able to design an engineered face mask here to constrain the speckle to be not Rayleigh, but non-Rayleigh, and have an arbitrary speckle PDF. So let's try to use these techniques. So here are examples of a linear Rayleigh speckle, and here a Rayleigh squared speckle. We designed one Subrayleigh pattern, which is this green PDF here. And here is an example of what the pattern looks like. We squared it, and we end up with this purple curve, which is a bit different from the Rayleigh, perfectly Rayleigh statistics, but we will see later that it's not that unfortunate. So we decided to run exactly the same simulations as before. You can recognize here the Rayleigh and the Rayleigh square that I showed you before. But we're going to compare Rayleigh and Subrayleigh, which can be used. These are speckles that can be used for the blind F3 with SRS. And you can see that the Subrayleigh is reconstructing even faster the cement star image. In the square PDF, so the one that we're going to use with the blind sim with cars, we can see that the Subrayleigh is pretty efficient at reducing the number of images needed to reconstruct the cement star. And if we have even a closer look, we can see that the Subrayleigh square is even doing the reconstruction faster than the regular Rayleigh speckle. But up to there, I didn't tell you all the truth. Indeed, indeed, we measured the transfer matrix between the SLM face mask and the object, the camera plane here. Indeed, we measured the transfer function, which is called here a transmission matrix, to be able to modify the Rayleigh speckle into a Rayleigh speckle pattern with a custom PDF. But if we want to keep the blind sim blind, we need to change a bit the experimental setup. If we were to add scattering, an unknown quantity of scattering here, we would have a slight change in the transmission matrix. And we need to have a look at what is the impact of this change if on the speckled PDF here. What I mean is that if this is Subrayleigh, is it still holding Subrayleigh, or is it going back to Rayleigh right away? So we cut the bulk into a multiple scattering, thin scattering layer, and ran a simulation about this experiment. And here is the result. First, I need to explain to you that we used the contrast as a proxy to estimate if the speckled PDF was Subrayleigh or Rayleigh. If the contrast is well below 1, it means that we indeed have a Subrayleigh pattern. If the contrast is getting closer and closer to 1, it means that we're converging back to Rayleigh speckled PDF. And as you can see here, the non-Rayleigh PDF is maintained at the beginning with a thin optical thickness, but it's converging back to speckled PDF. And for example, in biological tissues, usually the LS here is between 50 micron to 200 micron, which will result in a depth of maintaining, for example, 0.8 in contrast of about 15 to 60 micrometers, which is pretty reasonable for doing super resolution. Now I'm going to conclude this talk by summarizing what are the features of the blindnet 3. So we demonstrated that the super resolution method called blindnet 3 is label-free because it's using Raman scattering. It can be chemically selective because of the use of the coherent Raman scattering. Then we demonstrated that it was compatible in power-wise with biological tissues, and that it had built-in sectioning. Finally, by the use of blind SIM, it is resilient to scatter. In a later part, we decided to have a look at the possibility to improve even further the spatial resolution. But we decided to solve one of the issues, which was the sparsity of the speckle. To solve that issue, we decided to shape the speckled PDF to observe what would be the effect on the reconstruction algorithm. We demonstrated that the Subrayleigh PDF is indeed very efficient for inside the reconstruction blind sim, and that the speckled PDF is maintained over a reasonable amount of scatter. Before closing this talk, I would like to thank the lab team that was with me for these past 3 years, and also all the administrative team members, the people at the workshop, and also all the interns that worked on this project and contributed greatly to my work. With that, I thank you for your attention, and I'm looking forward to hearing your questions.
Thank you, Julien. Thank you for this very clear and informative presentation. So I suggest that we switch to the comments and questions, starting with the reviewers, and probably Emmanuel Border from École Polytechnique.
Okay, I can start. So I don't know if
Can you hear us, Dario?
Dario.
Yes, yes, yes.
Okay, great. I will try to speak loudly, but I have a mask on my face, so it does not simplify things. So first, thanks for proposing me to review this work. It was very interesting. And as a general comment, I would like to say that it's a very it was very brave to embark on this project because it's a very complicated technique and experiment, which, if I understand well, you had to build from scratch. And so when you start such a project, you don't know if it will end up going somewhere, and it did. So this is nice to be there. I appreciated the manuscript. I will say a bit more on this, which was overall clear, and your presentation as well. So it's nice also on such a complicated project. So I've now a few more maybe specific comments on the presentation and then some questions. So in the manuscript and in the presentation, your description of Raman techniques and super resolution is very clear, and it's nice to have that. And I guess the manuscript will be useful for other people in the group. So this is nice. One thing that your chapter on results and your presentation is very nice, but you hardly discuss how you built this thing here. And that's true. Just looking at the picture and knowing what it is to synchronize beams and put SLMs and everything, I can guess that this was not that easy. So maybe you could have taken a bit more time presenting that. I don't know, maybe you just wanted to forget about it and go to the results. But I mean, even in a manuscript, this is interesting information for other people. One critic I have in the intro is that, well, it's not, I would not say, I would not sell this technique like that, saying that fluorescence is bad and it is complicated and you have to design labels. Because if you want to sell this to biologists who use fluorescence, you will need to show them that you can replace fluorescence microscopy with this, and probably you will not. So more, you should think of it as a complementary method, which will bring different contrasts. And as for the super resolution, it's interesting to discuss the different options, but if you go to very high resolution techniques with label-free contrast, then you will end up with very small signals. So another argument is maybe that SIM gives you a reasonable probe volume and you can hope to still see things. Okay, so then I have a few questions. So one first very basic one, at some point you mentioned that you started working with plastic bead samples and then you moved to cells and tissues. And you noticed that plastic bead samples were more fragile than cells. Can you elaborate this?
This is I don't really have an explanation for it, but this is like I could run the full power with the biological samples, while with the beads it was more complicated. I don't exactly know why. It can be maybe because the plastic beads are keeping more heat inside them. They doesn't evacuate properly. Maybe with the, I don't know, the shell and everything. I don't have a proper explanation for that.
Okay.
If I can comment, were they in air or in a liquid environment?
They were in liquid environment.
Okay, because for example, in our case, when they are dry, they just explode very easily. When they are in a liquid environment, it helps dissipating the heat and they can sustain much higher power. But then if they're, in your case, in a liquid environment, then I agree that it's
usually they meet in hard water. So yeah, definitely they are inside the liquid. But yeah, it's an observation that we did, but this is the only clue that I have, is maybe there's a heat thing, because they also maybe the sample is very thin and it doesn't enable for the heat to dissipate. I don't know, but I could run full power on the brain sample.
It's important to know, because as physicists developing techniques, you typically want to work first with simple objects,
Yeah.
but maybe it's better to go right away to
Biological
cells.
samples. Yeah.
This makes things more complicated. So also about complexity, you first decided to work with SRS and not cars. And why is that? Because cars is more simpler to implement. Right?
Yeah. But one of the issue with cars, and we started with SRS because it was easier to do quantitative imaging. That was the main reason behind it, and not about the technicality. And one of the issues also for the cars is to adapt it with the blind sim, nonlinear blind sim algorithm, and also to distinguish with the artifacts raising from the cars.
Yes.
The non-resonant background mostly.
That makes
So
sense. But then the setup is even more complicated, and you have to debug all the experimental complexity.
But then with the reconstruction algorithm, we could not know if the artifacts were coming from the algorithm or from the car's images. So it made things simpler in our mind. Like we didn't have to focus on every aspect.
In your reconstruction, you assume that so you're using an algorithm which was designed for incoherent imaging.
Yes.
And you assume that although you are using coherent contrast, things sort of work the same. And for example, looking at this image here on the top,
yes,
the super resolution one, do you really think it's a real question that these are sample features, or could there be some speckle or coherent artifacts also?
Yeah, I'm trying to find
the slide 32.
Here, that's why we decided to do. Historically, we did the bead samples, the 250, the 239 nanometer beads before doing this this experiment, and it's that made us run this experiment where we use a lot of different size for beads to make sure that everything was working as intended in the reconstruction. Because here we retrieved, I don't know if it was clear, but we imaged with the several bit diameter, reconstructed the image. We note that the bits are aggregating, so they are in close contact, and we measured with the line profile the distance between the two maximum. By measuring.
I'm sorry, Julien, this is nanometer probably, not micrometer.
Yes, that's true. That's
okay.
Yeah, that's nanometer. And then when we retrieved this this distance, we were coming back to what is the nominal diameter that is set on by the manufacturer within the uncertainty range.
And this is this a 3D sample or mostly a monolayer of beads?
It usually depends on the bit diameter. When there are large bits, it's easier to have a single layers, but that's true that when we image this sample with the 239, it was so small that it was always aggregating. So yeah, here there are probably 2 layers. But we are really confident that these are really proper bit features, because also when we retrieve the distance between the two maximum here, it fit nicely the beam diameter. And since the SRS in this case is a perfectly phase match at all times, that's why we think that it can work with even with the incoherent algorithm.
Okay. Perhaps one way to test it, I don't know if it makes sense, but would be to run simulations, assuming that the sample is a point object, but also a plane or a line or a 2D or 3D object, and see how faithfully it would be reconstructed.
Yeah, yeah, definitely. That could help.
When you discuss the sectioning ability of the technique. This is interesting and important. So you show experiments with, so these correspond to different illuminated fields of view.
Yes, the different colors. The different colors. They, in fact, in the sample, in the setup, we have the SNM, and we set macro size pixels, and all these different curves, the red, the green, orange, and so on, they are for different size of macro pixels. So it means that the field of view, the speckle spread is bigger or smaller, and we see that there's this decrease in the sectioning ability.
Yes.
Of the blindness.
Is it possible to derive a simple scaling law of the sectioning? You know, in two-photon microscopy, it would be 1/z².
Yeah.
And I guess here it depends on the field of view and other parameters.
It depends on the field of view, and we tried here to derive a model for it. It kind of fits the experimental result, but there are some stuff that are not perfectly fitting. But it gives an overall idea of the sectioning that we can have. Like, I don't know if you want to have numbers, like you set parameters and you can get some sectioning instead. But here is more like the overall evolution of the sectioning with the Z propagation.
So I don't know if, I'm not sure, you did not, in your manuscript, you discuss about optimal speckles that could be designed to work at certain depth.
For the speckle PDFs?
Yes. And my question, so I don't know much about this field, and it was really only shortly outlined in the intro, but I was wondering, well, is it possible to design a speckle that would be adapted to the expected scattering?
Here we tried only a few possibilities, which were Subrayleigh and Superresolution with the speckle square. But I'm not sure that these are the optimal ones. They are a good solution that we tested and that was working. But the feeling that I have on these results is that what is important is to have a lot of medium intensity in our case, so medium intensity speckle, which means that they are Subrayleigh, but we could, for example, here you can think that maybe this speckle PDF that is not the one we tried could be even more optimal for the reconstruction, because here you have a lot of more or less equal to the mean intensities. And I don't know if we could find really one way to find the optimal speckle. I think it's more like a trial and error, and probably many simulation with many different speckle PDFs. But my feeling is that for the blind sim, what helps is the mean intensity. And but I was surprised at first that this. I was expecting the Superresolution, so more with a lot more intense, like the speckle square, to work better. But in the end, it's the Subrayleigh which worked better. And I found in the literature that, for example, for ghost imaging, they are using this non-Rayleigh PDF, and one paper showed that if you use a Subrayleigh PDF, it was working much better than Superresolution or Rayleigh PDF. There's something with the Subrayleigh PDFs.
Okay. Well, there really seems to be something really interesting to investigate
Exactly.
now. So it's nice that you got interesting in novel results in a new field, and also are opening new questions. So
okay, this was really interesting work.
I will stop my question soon because we have many jury members, and I don't want to dry over the topics. But Yes, this is very interesting. Probably one thing to take into account in designing the best illumination patterns will also be to minimize the number of images that you will need to reconstruct, because if you want to apply them to biological samples, you will have to consider this.
Yeah, especially if there's dynamic in the biological medium.
Yes, that's true. But also, you know, phototoxicity and illumination.
Right. Yes.
Okay, so
thank you.
Nice work, and I guess the second reviewer will speak, Mr. President.
Sure.
Thank you.
Thank you, Emmanuel. And so a nice time for Dario Poli to get the microphone.
Yeah.
Okay, can you hear me?
Yes.
Yes. Okay, very good. Okay, so I have noted a few questions. First of all, I would like also to thank you for the very nice presentation. I really enjoyed reading your thesis. It was very well written, and the topic is exciting because super resolution is, of course, a very hot topic, and there is plenty of room at the bottom, as they say. So improving the resolution of SRS and CARS is really a breakthrough. And it's not easy. So you performed a very difficult task, in my opinion. I mean, it's really hard. So my first question is the following. If you can go, for example, in slide 26, exactly here, you say the assumption for blind structural illumination is homogeneous illumination. Here, when you say about homogeneous illumination, do you mean that let's say, for example, you say that you did 100 or 700 images, the average illumination pattern over the, because of course one illumination with one speckle is not homogeneous in this sense. So do you mean that you will need to have an homogeneous overall on average after the average of 100 of images? Is that something that you require for the blind illumination or not?
Well, I would say is that the overall, the mean illumination has to be smooth because, for example, in our case, the illumination is not exactly uniform. It has a Gaussian shape because of the envelope of the beam. So the idea is more that if the overall the mean of this illumination, the speckle illumination, has a lot of variation, this will be propagated into the reconstruction.
Okay.
If it's very smooth, you will see an envelope, which is the envelope that I showed in the introduction slide of the blindness 3 principle. But this requirement will be fulfilled if the illumination is smooth over a large number of illuminations.
Okay, so in your opinion, when you say that you use the hundreds of images, why do you really need so many images? Is it because of this condition that you have to fulfill on average as you random the phase, so you random the illumination speckle, you really need to acquire in homogeneous illumination, that's why you need hundreds of images, or it's a different reason for the need of so many images?
I think there are two things, that there is really this homogeneous illumination, because otherwise, if it's not homogeneous, the root mean square of this inhomogeneity will be propagated back into the reconstruction algorithm. But there's also the noise issues. In the simulations, I didn't put any noise, so we don't see it, and we see that with as few as 100 images, it's enough to reconstruct the sample. But experimentally, and especially with the SRS, we have a lot of noise issues. And this can also be a reason why we need still a lot of images. But these are more like a practical limits. In the simulation, we don't see that.
So, for example, did you try to increase the integration time in the SRS lock-in, for example? So you acquire higher signal-to-noise ratio. Does it allow you to decrease the number of images or not? Because at a certain point, no, if you have an infinite signal-to-noise ratio, you still need many images to do this homogeneous illumination. Do you try to change the integration time?
I played with the integration time, but I didn't really run experiment comparing how many images that I need to use. But what I would say that there's really some kind of a trade-off that I observed experimentally, meaning that if we go to too high integration time, in fact the sample moves and then the image gets blurry. So it needs to be not too fast, not too slow. But definitely we played with the integration time a lot, but we didn't run exactly the experiment that you're mentioning.
Okay. Yes, I see. Okay, then I have another question, which is somehow a bad question, so don't take it too badly. Just I'm trying to do the devil's advocate. In the introduction, I like the fact that you say, well, I have to deal with scattering because the sample is scattering. So here, this mouse is a heterogeneous medium. So somehow, even if I do structural illumination, it will not be any more structural at the end. Okay, yes. And so you are using a speckle pattern.
Yes,
but that's only true for the pump and not for the Stokes. No, yes. That's something that you did not discuss. I think at least I did not find a proper discussion in the thesis, which goes in the other direction. Because of course, if you really want to go deep, both beams will be scattered at a certain point. So, did you think of a way of using both beams as a speckle? Is there a way or not?
I tried to think about that, but I didn't find a solution to have the two beams as a speckle. But the answer that I would make is that first we used as a speckle pattern the shorter wavelengths, so the one which is more likely to get scattered. And second, when we do super resolution, usually most of the technique, if you don't have an active correction for the beam shape, you're losing the super resolution feature. For example, for STED, very quickly, the donut shape, if you don't have any active correction, it will not be a donut shape anymore. So it means that usually super resolution are done at shallow depth. And our objective with this technique is to go at intermediate depths and to try to go a bit further than other super resolution method. But we didn't find a way to have the two beams as a speckle.
Okay, because of course, I mean, this will be important. Otherwise, you cannot really go deep. Yes. Okay. Then, so I somehow agree with Beaurepaire about the image. If you can go back to slide number 32. Okay. While on the next slide with the HeLa cells, it seems, totally, it's very beautiful. The result is very clear that you can observe a structure with the blind S3 while it was not possible with conventional SRS. Here, I really find it difficult to agree with your conclusions somehow, because here, for example, you made a cross line across these two beads, okay, which is very nice. But around the beads, it's really hard to, let's say, to tell where the other beads are, okay? Because it seems like there are some kind of, I don't know, airy discs around those beads or other structures. So maybe, as you said, it's a multi-layer structure that you just need to find a place where you have just one layer. But it's really not convincing to me that here these two bright spots are indeed two beads, two polystyrene beads, and not just a kind of interference between some patterns that shine as very bright. Do you have any other comment to convince me that these are indeed beads, or a way, I don't know, with a electron microscope to image the same sample? I don't know.
I don't have a higher resolution image of this location, but what I would say is we can see several things in this image. We can see that there's with a conventional SRS, there's a better sectioning. This is what you can see when you compare those two images. Here we can barely see maybe the layer which is probably beneath it. While when we use the blind 3, the section is more loose. So it means that maybe we are getting some signal, SRS signal, from the bottom layer. And there's also one thing that I mentioned before is the Gaussian envelope of the speckle. The Gaussian envelope of the speckle makes it sometimes a bit harder to compare the two images, and that's why we run this bead diameter experiment when we did the linear XY plot, is because we wanted to make sure that what we reconstruct is we are pretty confident that this is working properly.
Okay. So this brings me to the next question, which is about the Gaussian envelope. So your Gaussian envelope is how big is it? You can vary it, right? How many micrometers? It depends on the number of pixels on the SLM.
Exactly, it depends on the size of the macropixel that we design on the SLM. We can be as small as the PSF, and we can go with the microscope objective that we have, which is 1.27 NA. It can be like up to 5 micron is quite common for us. But then, if you want to improve that further, you can use spectral focusing. There are some solutions that I discussed in the manuscript to even enhance further the signal to noise ratio and improve the field of view of this of the blind 3.
Because my question is now, if you want to have both a high spatial resolution but also cover a large image, is it possible to do tiling, for example? Did you try, or do you have any idea how to do tiling with, we have to sum up different Gaussians one after the other?
To do some patches, yeah.
Yes.
I think it would be possible to do several patch of super resolution images. The issue is how to combine the different patches, because always on the borders of each image, it would be maybe a bit complicated to fuse the information. Mostly the trade-off is the field of view with the sectioning, and not the spatial resolution, truly. It's more that if you increase the spread of the speckle, the sectioning will be more loose, more than a degradation of the spatial resolution.
Yes. No, because in our lab we are also trying to do wide field coherent Raman setup, and we also have the problem that the illumination is not homogeneous. Of course, it's a Gaussian or something like this. So I was wondering if you tried to compensate for that. So even without doing the tiling or patches, for example, this image on the right-hand side of the screen, you could calibrate for the Gaussian envelope, divide by the Gaussian envelope to normalize. And then, of course, at a certain point, you have to cut the borders, because otherwise you divide by 0, you have just noise. Yeah. Did you try to do that in order to normalize or not?
Yeah, but if you do so, you are going to increase a lot the signal to noise ratio on these outer parts. And I'm not sure that then the reconstruction algorithm will work really.
No. After post-processing. So after you get this image on the right, okay, then Now you want to somehow have the same intensity as the one in the middle for conventional SRS, of course, with higher spatial resolution. So you can use the one on the left to calibrate for the Gaussian envelope on the right. And so if you normalize the one on the right by this Gaussian envelope, you get the same as in the center. Then, of course, you have to limit, because after a certain distance from the center, you are divided by something which is too small. And so you have a so poor signal to noise ratio that at a certain point you have just noise. So you have to cut.
No,
maybe that's a suggestion for the future.
We did not do it, but that's true that it could be a solution. But it also means that for this image, we know that the quality of the reconstruction is a bit worse here. If we are doing calibration, we might be in a bit of in the fog and not completely sure of if the reconstruction fidelity can be high or not here, because there's if you divide by the envelope, there will still be an increase in the SN in the signal to noise ratio if you go further from the center of the Gaussian. This will not be avoidable.
A decrease, not an increase.
A decrease in the fidelity and an increase in
yes.
Yeah,
ratio. but even inside the circle, where you say that you can trust your data, maybe it's good to make this normalization so that you have inside the circle, you have a flat pattern, let's say. Then it's up to you to decide where to stop. That's a suggestion for the future.
No, that's true. We can define some threshold, high threshold to normalize the intensity. That's true.
Okay. I think that I have just one last question for you, which is the following. I would like to hear from you with your words if there is an easy way, let's say, without formulas, to explain to a stupid-minded person like me why using a speckle pattern you can somehow increase the spatial resolution. Okay. In a way, if we go with the standard SIM, okay, you can say, the explanation is very clear, no? That you illuminate with this pattern. So the pattern is like a sine wave with a certain K. So you project the central frequency outside, and so you detect the other frequencies. That's very good. Now, with is there a way to use this or a similar reasoning to explain in an easy way why using a speckle illumination you can achieve a higher spatial resolution? For example, I can imagine that each speckle feature is not sub-diffraction limited, right? So
diffraction limited, yes.
It is diffraction limited. So it is not because you are illuminating with something which is smaller than what you can do with the standard illumination, but it's something related to the frequency pattern of the speckle, right? Exactly. So can you explain in a similar way somehow?
I think we could explain it in a similar way, but it would not be perfect circles like that in the Fourier domain, in the spatial frequency domain, but it would be more something randomly spreading in this domain, and that also can be a reason why you need a lot more images, because you don't exactly know if you're several times gonna explore the same region in the spatial domain, but it's exactly the same principle. It comes from if you Fourier transform your excitation in the Fourier domain. But yeah, I'm coming back to equations, but it's the same thing. It's the fact that the illumination is not homogeneous, but it has spatial features which are close to the diffraction limit and that are here random. And this is making the number of illumination acquisition, the number of image to acquire higher. But it's, in my point of view, it's exactly the same explanation but instead of being two nice circles, it's more something random. That's what I would say.
Okay. And while with the standard structural illumination, you have also, I mean, both high and low frequencies. Here, it seems that the speckle has only high frequencies.
Yes.
Is it true? So I imagine that if you Fourier transform on the right, you don't have circles, but you have random, but they're somehow on the side, not in the center. Do you lose something in the center for smooth low frequencies, or not?
I think I saw that in one paper that yes, indeed the reconstruction here for this point is much lower than what you could. It's lower than what you could have with the structured illumination, perfect structured illumination. That's one feature of the spectral illumination. Yes, yeah, I think
okay.
is not, as high in this part of the Fourier domain.
Okay. I think I asked all the questions that I have on my notebook, so I think I can stop here. Thank you very much for your replies. They were very clear. Thank you very much.
Thank you.
Thank you, Dario, for your comments and questions, and thanks to both reviewers, actually. Now it's time to go to the members of the jury. So I will start with Alexandra Fadula from the SPCI.
Thank you, Mr. President. First, thank you, Julien, for inviting me in this jury, and thank you, I was very pleased to read your manuscript. I'm not so familiar with Raman, so I learned a lot. Thank you for that. I really appreciate also the presentation. It was very clear. Thank you. I also have a few questions. I should say that, yes, first I wanted to congratulate you because you made a work where there is a simulation, you built a microscope, and you made also the algorithm to reconstruct the lines in images. So this is a very nice work. I was a bit frustrated because the part on the microscope on the experiment was very short.
Okay.
So even I could think that it was very easy to build. I know it's not the case.
No, it was not. It's true that it didn't develop too much, maybe.
But as you didn't mention all the problems you met, you could think that it was easy. Probably not. So maybe I can ask a few questions on the experiment. So I even didn't know that you built it from scratch. So I had to ask. So don't forget to tell.
Okay.
That you made all the algorithm, all the etc. So,
okay.
My first question is, so you have your speckle and you need to acquire many images to be able to define an image. And so you made some tests in the last chapter. So it was very nice to see different images reconstructed with different numbers of acquired images. But my question is, how do you decide with images you obtain on the cells and the brain?
Okay.
How did you decide the number of images you?
It was more a feeling, a try and error. At the beginning, I was acquiring a lot more images. I was more about 250 or 300 images. And then I realized that the reconstruction could be worse because, in fact, the sample is moving. So then I reduced the number of images to 150, 200, and usually the reconstruction were much better, probably because this sample was not moving. And
moving, but it's fixed, right?
It's fixed, but then there's the heat that can make it move, especially that it's in water. So then there's this convection movement and.
And when you say it's better, it's a personal feeling, or do you have a quantitative?
It's more like when we do the reconstruction, when I play with the different parameters, because in the reconstruction algorithm, you have 4 parameters to optimize. And then and when I'm at the very end of the reconstruction, I can say, okay, maybe it was too many images, or and I can yeah, like assess more by the result if it was too many, and then it was more in practice that I
Okay, but
realized
you don't have any quantitative
No.
Okay.
no, it's more like by eye you see that the reconstruction is really bad, or it kind of makes sense.
And how long does it take to make the reconstruction?
Oh, this is pretty fast, because also we don't have a camera, so that we are doing a pixel by pixel, so we have a limited number of pixels. Most of the images that I show here are 64 by 64, so that they are rather a small number of pixels. And this is pretty fast to reconstruct. And I didn't optimize too much. I'm not running a GPU. I'm not. It's really not optimized. The code is really not optimized, and it's not what is limited. It's a few, maybe not even 1 minute. So
would it be possible to reconstruct during acquisition and have an objective criterion and say, okay, now it's okay, and I can stop the acquisition?
I think that could be better than what I do, because usually I take many acquisition, and only by looking at the several realization, I can more or less say how the reconstruction will be, because I can see more the SNR on the computer, and I see if all the realization makes sense, if it's well spread over the whole field of view. And then yes, I run the experiment, but sometimes I run it the day after, and yes, that would be of a great help, I think, to have something, a pipeline to reconstruct.
Because you say a very important criterion should be that the whole sample is illuminated.
Yes.
So this could be very easy to follow.
Yes. Yes, I could have a
time and say, okay.
That's true that I could plot the average at the same time as on all the acquisition. I didn't do it, but I think that would help a lot.
Have a stop,
and the stop criteria, maybe.
Okay.
Yes.
Because if you are imaging a light sample.
Yes. For light sample, yes, definitely that would be much better.
Okay. Yes. And I was also wondering, so I was really impressed when I understood that you made the code to reconstruct, because I know that it can be not so easy to have a code for SIM. Did your code, could it be used for classical SIM, or no, it's dedicated to Speckle, right? Could it be used
I didn't try. I didn't try. I think it would not be optimized for the SIM, so maybe we would need more illumination because it's not using the a priori knowledge. So I think you might need more images, but I don't see a reason why it should not be working.
Sorry, because I will ask to go back to the slide number 32, but in your image where we are,
That's the main slide.
Yes. So just to, could we imagine to make a classical SIM with a grid on the same sample and reconstruct with your algorithm, or with an open source algorithm, because you can find an open source SIM algorithm to reconstruct the images. So you wouldn't have a ground truth.
Yes.
But you should compare.
Yes. No, definitely.
Yes. With your blindness.
No, that's a good idea.
A good argument to say, okay, it's a real.
No, that's a very good idea that we didn't have back in the days.
Have artifacts in classical SIM, so be careful.
But yeah, we could imagine to shape the speckle into a sinusoidal pattern. That's completely true. Yes.
Shouldn't be that complicated.
No.
So maybe you could compare.
But maybe no. I was thinking about the sectioning issues, but no, that would be the same.
You can make a 2D sample with your bits, and
we had a hard time doing it.
That dimension at the beginning. So yeah, with the size of your pixel on the SLM also, so
Yes.
if I understood well,
Yes.
the smaller the pixel on the SLM
Yes.
and the bigger the field of view,
Yes.
but you have less section, right?
Yes.
But is there any consequence on the number of images you have to acquire? Because if the it's completely, I'm not sure I understood.
No,
The number of images you need is
Yes.
it only depends on the
it only depends on the speckle, and it should be like it will increase because maybe the SNR will be dropping because the energy will be more spread over the whole field of view. But in theory, that if we could keep the same SNR, it should not increase the number of images required. But yeah.
Okay, so if you can if you can increase the power of the laser,
For example, yes,
more or less.
we were at full power, but
Yeah.
if we imagine that we have a laser.
Okay. Yeah, what I really, well, I said I was a bit frustrated about the setup because what I didn't find is the little information about how critical is the alignment.
Yeah,
especially.
very
So
sensitive.
You're talking about this this problem. Everything has to be well aligned, but you don't say at what scale, on a nanometer scale or a few hundred.
No, we have this stage for the temporal overlap because it's more difficult to find the first time the time overlap, and then to maintain it every day. It's not that complicated, but we optimize every day. When I switch on everything, I put an oil sample because I know that it's.
So you mean you move the delay, right?
Yeah, I move the delay line, and I can first I make sure the alignment of the two beams is the two beams are overlapped, because I'm using a leak backward that and on the camera I can see just the index mismatch between the glass, the cover glass, and the water in the sample. So I observe the back reflection. Then I can align the two beams spatially. And then I use the stage to there are two stages, one for the blind sim and one for the SRS. And then I just have a regular Torlabs. And it's okay for most of the day. Yes.
Okay.
No, it's pretty stable because we have the table is mounted on air, and everything is made so that it's pretty stable. And if usually every day I check the signal, but usually it didn't move or it moved slightly. The most what moves the most was the spatial overlap, but with the SLM, because the SLM, when it heats up and everything, the phase mask or the thing holding the phase mask is not completely stable. So this was more the issue. The rest was pretty stable.
But you can't go for a week on holiday.
Yes, and then you have to realign, but
okay.
but you can go on holidays.
Okay. I really like the last chapter where you try to let's say shape the speckle.
Yes.
Emmanuel maybe ask a similar question, but maybe I didn't understand well your answer. But so you want to shape your speckle, but I was wondering, did you have an influence of the object itself? Because if you have a very sparse object,
yes,
then you won't have a speckle everywhere. So would it be interesting to take into account the structure of the object itself when you shape your speckle?
You mean to find, for example, the optimal? Yes, definitely. I think that would help. But the thing is that you need to know more or less your objects, and if you only know that it's sparse, for example, if you know that. If you know that it's just, for example, sparse, maybe there's one speckle PDF that could be the optimal for this this solution. I would not know which one. I would say something again Subrayleigh, so that it's more or less homogeneous and covering the whole field of view. Because if you go for a higher contrast, so more in the what is called Subrayleigh speckles, you might have a hard time illuminating the very sparse part of the object. Yes.
Here you always tried samples that were quite big, quite.
In the simulation, I always used that object.
Yeah, yeah. But I mean, you have information everywhere.
Yes.
In the image.
Yes.
And sometimes sim is more complicated when it's fast. But maybe with Raman, with SRS or cars, you have information everywhere in the sample. It's not always the case in fluorescence. But
I think it's similar, so we might have a very sparse object. But yeah, since we did this work only in simulation, it's hard to tell for a very sparse. I didn't try a sparse.
the first step of the algorithm is to estimate the speckle, right?
Yes.
And if you
It's
have a very sparse
first to
speckle
estimate
image,
the object, and then we estimate the speckle, the illuminated speckle. But yes, like when if the object is very sparse, we might have in the reconstruction only one dot or nothing if the object was very sparse, and also the speckle is Subrayleigh, for example. Yes, and that would add a lot of noise probably in the reconstruction, and that could give a hard time to the people reconstructing.
Yeah, you show a very nice image of the brain with your blindness screen. Yes. So you have a sectioning here. It's like 10 microns, something like that, a few microns.
I don't know exactly the width, but
the slice is 100 microns.
The slice is 100 micron, but we are not going that deep inside the tissue. We are more about 8 micron deep inside the tissue. But it's true that in fact we realized that we had sectioning when we were doing this. This is the sample that made us understand that we had sectioning in the blind sim.
So that's why you can explain that in the blind sim image, the background is darker, right? It's the same color bar.
It's the same color bar. No,
it's the same scale for the two images.
Yes.
Because the background seems darker for the blind image. So I was wondering.
I think it's more that
it's because you have sectioning here and you don't have in the conventional SRS image.
And also this is a very close up. It's really close, and the resolution improvement makes it so that the signal is not blurring everywhere. If we were to have a larger field of view on these two, probably because here we start to see like that it's really dropping as well.
In the profile.
Yes.
Profile, it's your pics are sharper, but
yes,
the background is lower also. So.
But it's also because the resolution is.
I'm not sure it's on. Yeah.
But
it's hard to discriminate sectioning and
in general, conventional SRS has a better sectioning than the blind sim. Like the blind F3 cannot reach the sectioning of the conventional SRS. At best, it would be equal, but it will never be better than blind F3. Except if you use a temporal focusing or something more. But it should not be a better sectioning than. That's why I think it should be spatial resolution improvement. And not sectioning necessarily. So
you didn't try to make a 3D imaging?
I tried I tried many times, but I didn't quite manage. And I also tried with the Price time and bits. but also it was very hard. We didn't have exactly it took time for us to have the right stage, so it took a long time. And I think
It's not working, or it's
no, it's more that it was more interesting for us to show that it has sectioning, but fundamentally than to really show a bit structure in 3D. And then because we had many things to run in parallel, then we didn't go back to it, but we could have, because then we had some piezo which arrived, and it would have been much easier to do and to do like enough steps in the Z direction, because in the manuscript there's one image of several bits, but it's not as convincing, I think, for the sectioning as the curve with the oil, thin film of oil moving up and down, which is really, I think, the key experiment to
so it should
prove.
work.
It should have sectioning, yes.
Okay. All right. One last question on so the last experiment. Well, you showed the simulation where you propagate your speckle through a scattering medium and show that. Yeah, here. So here it's a simulation, right?
Yes, yes.
So I just thought, but what did you do the experiment? It sounds very simple compared to the rest.
Yeah, but
Should it be interesting, or?
yeah, I think it should be interesting to do the experiment, but I was running out of time, I would say,
Okay.
and I didn't do the experiment.
Okay. And you compare the contrast with LS.
Yeah,
Is it LS the good parameter, or should be the LT, because in the biological sample, as G is almost 1, would it change something, or?
We decided to go for LS because even a slight move for example, the PSF for the SRS, and we will not have a signal,
Yeah, right.
and not even a
It's not
transport.
intensity.
Yeah.
Okay. Thank you very much.
Thank you.
Thank you, Alexandra. It's time for Sandrine Levecfort from ISO CELEC.
Thank you, Mr. President. Thank you, Julien. Thank you, Sylvain, for inviting me for this PhD defense. I'm not super familiar either with Raman, so I don't know about some more super resolution, but from the other side, the fluorescent side. So that was super interesting for me to read your manuscript, which I enjoyed a lot because it was quite well written and compact.
Thank you.
So, and then I also really enjoyed the defense, which was super clear and complementary with the manuscript. So congratulations for that.
Thank you.
So I will still have some questions, even some are already been addressed, but maybe I will try to find the one that are not been discussed already.
Am I putting the slide 32? Or?
Yeah, I think I will go to slide 2 at some point. Yes,
Okay.
you can put that this one.
Okay.
I think we all like bugged on this one. Yeah, so one thing maybe I was missing when I read the manuscript was the final targeted application, to know if you wanted to go to live cells, fresh tissue, and in order to know if you want to, to know the constraint of the acquisition times and the number of images. So that's something that you somehow address. What was and at some point you mentioned the mid depths, which so you could comment on what was exactly your goal or you were.
So first we can think of we try to use the blind F3 on plankton samples, which have a very hard shell, so it's very scattering, and to image that and to do super resolution in that would be useful, and to have some scattering resilient super resolution technique would prove to be useful. And then the rest of the question was for like
for
in
the
general.
Timing, if you want to do live or fixed, so then won't have the same constraint on the acquisition time and how many spectral imaging will need.
Okay.
These kind of things.
Like, since we basically usually we are limited by the amount of a signal that is the sample is generated, so it's hard to answer, and also the number of a pixel that you want in your image, because we are scanning technique, so we're limited by all these parameters. That's why usually we do a close-up on some region of a sample. Yeah, that's yes.
So when you start with your introduction, when you got three family of super resolution microscopy, in the structural elimination family, I was somehow wondering if you also consider the ESM, which is more like a technique that reallocates
Yes.
the position, which is something that is more in between for
Yes.
me, structural elimination and localization. And I don't know if you at some point considered this approach as a solution or not at all.
In fact, in the algorithm that we use, there's one part where there's some reallocation of reassignment of the pixels. So usually I don't use it in the reconstruction algorithm because I didn't really see improvement using it. But I don't know exactly where I would. Maybe there's a need for a fourth category in the.
Yeah, because it's kind of, you can see it as
Yes.
you also have a stochastic excitation.
Yes.
It's not stochastic anymore. You know where are the points, but you
Yeah.
isolate the point that will
Yeah.
give you an answer, and you can decide to the density. So it's kind of in between. So
Yes,
I don't know if it would work going to this direction, because you already have the DMD and the SLM.
Yes. No, that's true. I don't know exactly where I would put it, but.
Okay. Okay. Then I was. Yeah, so 32 if you want now. So yes, I was also confused because for me, I mean, you know, we prepare bit samples every day, probably twice a day, and they are always super flat. So for me, it was one single layer of bits.
No.
So no, not in your lab.
No, but we tried. We tried to have single layers with the 239 nanometer protein bits, but we did not.
Okay.
We didn't have the correct technique, I guess.
Because otherwise, I was like you, I was like thinking that the dark part on the SRS was nothing, and then it appears like reconstructed in a blind S3, so it looks like a common artifact in the reconstruction that we can find in SIM that would attend blind SIM. So I didn't really figure out that it would be out of focus information.
No, I think it's out of focus information, but I think we would be interesting to know your techniques for the. I think Leah, for example,
some bits and a very little amount of bits and some PBS, which make them stick all of them on the cover slip, and then.
And that's it.
Yeah.
Okay, interesting. We didn't know, so we didn't manage to. We wanted to make a one layer sample, but we just didn't manage.
In the good concentration.
Okay.
So while we're on this slide, so yeah, so as you discussed with Alexandra, there is this important question when you want to evaluate the resolution, which is something. There is in the localization microscopy, and maybe you can borrow also some tricks that have been developed for localization microscopy, which because we have the same problem. We never know. You don't know how many speckles you need to use, and we don't know how many images we need also. So there are some people that develop a strategy when they do a first image, classical image, and then they calculate a Fourier correlation during the acquisition, and then at some point you can say that the resolution you can get won't be better than that, and you can stop.
Okay.
So that's kind of tricks that you can throw away or stop the acquisition. Because otherwise, we used to do that a lot to try some profile, which kind of sometimes cherry picking and finding a good region. So it's even easier for you to say, okay, I'm completely blind, a nice sample,
Yes.
fully blind,
Yes.
and you calculate the correlation, and then you show that you are having the good resolution. And
That's true, because I think I spent a lot of time taking acquisition data and then going to the computer, try to reconstruct,
yeah.
see that nothing was correct, and go back to. I spent a lot of time doing that. So like I think that would definitely help for. This is something that I didn't build for the setup.
Live system.
Okay.
It's normal with C.
Yeah. So, alors, yes, about the Gaussian excitation. So, yes. So here, clearly, it's again, we have the same problem in ionization microscopy. So, do you think it would be possible? That's something we're trying to do. In fact, you could also think of scanning, because your system seems to be too simple. So you can think also scanning at some points the Gaussian
Yes.
speckle beam
Yes.
roughly,
Yes.
and just be always in the center of
In the next scheme of the setup, it's I think it's implemented to have this galvanometric mirror before the DSL. Yes.
Okay.
That's
Okay, so that would be
with the next setup. There will be a more powerful laser and scanning with the DSLM.
bien, je pense.
And it's pizza.
Okay, so everything is ready already. So yeah, so you're already changing this cell, because here it's a problem on this image, and then on the cell image on the ELA cells, it seems to be. I mean, I have the feeling that we are not like bothered by this because it seems fairly uniform. So it means you could play a bit on the huge one here. It seems very uniform to me. It seems to have nearly the same level of signal everywhere.
No, I think we can
or maybe on the
like here, for example, we can see that it's probably centered here, and here it's decreasing on the sides.
Okay.
But also like HeLa cells and lipidic content here of the HeLa cell is very intense. So this was a lot easier to acquire than the pre-7 bits.
So I was wondering if you were, because you mentioned that you are also playing with the field of view, or if you could afford that on this typical sample.
Yeah, definitely. Like I think on this sample, probably the field of view was a much larger because the signal was very intense with this lipidic content from the HeLa cells.
Okay,
yes, definitely.
That's
also something compared to the polysaccharide bits.
And then for the slide on the sectioning, so I don't know if it was 38, no, the one when you have, yes,
the one
multiple,
just before.
yes, this one. So I'm not sure I fully get your answer. So
yes.
Here, what are the different curves you can
Okay, so this was just theory and we use this formula. And in the experiment, what is very important is to have the thin film of oil with this, which is much larger, and which is larger than the waist of the two beams. This is very important. First check, and then for every position in Z, we acquire the signal which was generated because of the thin film of oil. If the thin film of oil is, for example, here, so out of the focus, we will be in one of these regions where the signal is pretty low, and this is what sectioning is. I don't know if I answered the question.
No, so this I got it. The different color.
Okay. The different colors is the field of view of the speckle.
So it means you not only change the width of the field of view, you change the size of the speckle grid.
No, I only the only thing I did is to make the SLM macropixel larger, so smaller, so that the speckle the Gaussian was was bigger, and all the curves were acquired, but one after another. But we were just playing with the field of view. the field of view of the
Okay,
speckle.
just the field of, not the speckled grains.
No. It was yes, because we don't change. We eliminate the SLM and we never change the position and the size of that for all of the.
Okay, I was wondering if you were changing within the backup at your objective and having a different NA, so different pixel size.
No. We run this experiment with only one objective, and we just change the macropixel size. And this is why we set different color, and we can see the evolution of the sectioning with the field of view. This is what to prove that okay, we have sectioning, but if we want to have a larger field of view, because that's always what we want, we have to pay the sectioning. Yes.
Yeah, we used to compromise. The rest have some questions left. Yeah, so within your setup, so you have this, you have the DMD to generate the blind scene cell, the blind scene beam, sorry. And DMD, as you mentioned at the end, it's not super efficient. So, and then it's also very sensible on the wavelengths, so you want to select, and you will need to realign depending on the wavelength. So I was wondering, because okay, we see.
I was searching for it.
So I was wondering how, because the whole goal of, because I find very smart that you combine a single point scanning with a wide field. It's not usually done. So here you can still do spectroscopy. So I was wondering
exactly.
how DMD would be so easy to use if you want to test the spectroscopy, but it might not be the beam information.
To do spectroscopy, we just would need to select a different part here on the spectrum, and this was meant to be used for spectroscopy at the beginning, but we mainly used it to have a picosecond pulse, to have a longer pulse for the Raman, but we could also use it to target different parts of the Raman spectrum.
So you already pre-align your DMD because it has different diffraction angles. So you pre-align your target.
This took me some time. That's why I didn't elaborate too much in the introduction, but I made a section on the DMD because this was kind of a critical to
So while we're there, then within your conclusion, because I don't actually have some questions left. So you mentioned that you can add, because it's too simple, temporal focusing. So you said how you're gonna think of like adding that within there, and what would be the. So you want to increase sectioning, right?
Yes.
And some 3D. So how you want to.
I think we still have some place, some space. We have some long delay lines. I'm sure we can put something in it. We have like 1 meter delay line, so I think we could imagine to put something there. And also 3D setup could be useful.
And maybe I have a last question, which I don't really know the answer at all. So for example, in the approach that is also used by Anderson Fleck in Marseille, blind scene, they also now, so they use this random elimination, but they on top of it use the fact that the fluorescence can fluctuate, kind of Sophie. I don't know if that would be the case for because it's coherent signal. Does this, I don't know, does this also can fluctuate a lot because there's intrinsic change within the excitation? So I don't know if it would be also a way to gain a factor square 2 again, like they have now in this approach, and if it would be, because it's coherent, not improved. I don't know if that would work also to have this kind of.
I'm not very familiar with what they did in Marseille with this, so I don't know exactly how to answer the question.
It was an open question.
So it's a fluctuation of the emitted fluorescence from the emitters.
They both use the random elimination and on top of it the fluctuation of the fluorescence. I don't know if the fluctuation here would appear also so nicely because it's a coherent signal.
So I think for cars it could be used because this is the way it's detected. It's more or less similar as fluorescence. But for SRS, it's since we are measuring a small delta on top of a mountain, the pump, and because we use the lock-in and everything, I think we could not use it in the SRS case, but in the cars, definitely. I think that's the answer that I would make.
Okay.
That cars okay, but not SRS because of the lock-in and the way it's detected.
Okay, thanks a lot. And, great question.
Thank you.
Thank you, Sandrine. Now it's time for the advisors to speak. I guess that we know everyone who has no questions on slide 32. Right, but I would still like to see it while I comment.
So maybe I can start. So yeah, first I want to really say that although I am the official PhD advisor, I'm only by name, and this is really Ethan's supervision and Ethan's project, and I've played a minor part in all of this, and it's really a impressive experiment that you've mounted in your PhD, and it's a really nice mix, I think, of the technique that we've developed for the past 10 years around waveform shaping, complex media, with everything that Ethan brought about Raman and nonlinear microscopy in general. So it's really a nice blend of our two expertise, but I played a very little role in all this work except discussing now and then. So I'm really impressed by what you did, and I take very little credit. And I think it's also need to be mentioned that you really went from this really blank, almost blank optical table, just a laser was there and some very simple things, all the way to biological samples, which is very unusual for the team. So congratulations on that.
Thank
you. Definitely, I think you showed with this slide specifically that you're a very skilled and persistent experimentalist. It is a very good quality as a researcher. And I will leave, of course, Ethan say more about the work itself. But I think as a team member, you've been really a great person for 3 years, very helpful for everyone, very positive on all circumstances. Of course, I guess you would say something about COVID, so I won't comment on that. But you've been really a very great addition to the team. So I really want to congratulate you for all these 3 years of work, and wish you, of course, all the best for the next steps in your career. So,
thank you.
Thanks.
Thank you, Silva. First off, happy birthday.
Thank you.
The first thing I need to say, being a non-permanent at that time, so I was very lucky. I was very lucky to have Julien as a PhD student. It made my life much easier to have someone skilled in the setup. So I had only to teach Julien for a very short time, online setup. I showed him some stuff that was on the table. It said I didn't like it. I'm gonna rebuild it, and he did that and made it much better. This is basically one of the most let's say striking feature that I found in Julien. He was very persistent. Everything, and very tiny screw all the way to the alignment of the laser, to getting his data done, to the analysis of the data, to writing the code. So in that sense, I was very lucky, right? So because the first year there was a lot of, by the way, together with his PhD, he also did the Collège de Général. So there was a lot of lecturing to be taken there. So the first year was heavy, but the second year onwards, Julien was basically almost alone in the lab. Fooling around with the laser, aligning, getting the signal back. So this was for me very. It's a bit let's say egoistic, but it was very easy for me in the second year, right? Which I think everybody recognized. This is not a simple experiment. So we mastered it with an extreme fast pace. This is again, congratulations on that. So,
thank you.
Very skillful experimental physicist. So he went to the Photonics West with his very first preliminary data. Got very excited. We went together there. He comes back with a lot of blood in the eyes, as you say in Brazil, like very excited to do more experiments, do more ideas. COVID. So we had to stop the lab. We had to stop experiments. And this was, I think, was a big, let's say, a big slowdown in the motivation, I think, for everyone in the world. So there's a lot of we should take this. I think there could have been a lot more than we thought in the beginning, right? That we do, like the spectral stuff. But due to the COVID, we had to slow down more and do this very simple, I mean, very complicated setup, but still a very simple proof of concept, fundamental proof of concept key that I think I was happy to see that Julien in the end embraced it. Right, he understood, and he was even angry against the reviewers, right? So I could see that you really embraced the idea. That in the beginning, perhaps less, and then bit by bit, you were really taking this with you. Another thing that was very hard, he was alone, basically. I mean, the lab was big, but it was the first project on Raman in the group, right? Absolutely, yes. Superresolution as well, new for me. SRS was new for me. I did scars and so on, but SRS I did a very little bit. And Julien really quickly put up the setup to really like state-of-the-art sensitivity. And the power that, I mean, Julien was very picky about every single thing because he was always at the maximum power, but it's not because he was cranking up, it's because it had everything we had. Right, so we only had like 30 milliwatts at the end of the objective, and that's what you reach. So you've proven yourself to be like a very skillful searcher. I'm very happy to have you in the lab to have achieved this. Yeah, so
thank you.
We have a long road ahead.
Thank you, Luca. So I guess it's time for me. I would definitely concur with most of the comments which were made. And, the manuscript is really nice. It's extremely clear. Covered a very broad range of subjects. This beautiful setup. I also concur with the minor reproaches, which is you should have told us what doesn't work in this experiment. But of course, it's really hard. And since we recently mentioned the spectroscopy thing, I think that one thing which you really downplay in your manuscript in your presentation is that the Raman spectroscopy is really specific. And this is something you could probably highlight more.
Yes. Some posters I compare the spectroscopy between the ability to select one mode compared to the fluorescence mode and what I said in this talk. Usually I stress more this point.
Okay. And so very quickly, how long does it take to switch from one wavelength to the other? I mean, taking into account possible realignment or whatever setup.
What do you mean? Like if I manually change the OPO, for example,
from the lipid band to whatever.
It can be very quick, like a few minutes, I think. In matter of few minutes, if I know where the bands are with the spontaneous Raman spectrum, I just compute. I know what to put on the OPO, and it's really quick to realign. And if it was to address different bands with the DMD, it's very quick because the DMD can be up to 10 kilohertz. So that can be very quick with the if it is within reach of the spectral band of the excitation spectrums. Yes.
I have another quick question, hopefully, because somebody mentioned it, and I'm not sure I understood it. So the RIM technique from back in this 3D, your technique, is there a fundamental difference between them, or I'm not sure I got that?
I think the reconstruction algorithm, I'm not very familiar with the RIM, but we discussed with him, with one of the PhD students at the MIFOBIO conference. I didn't, and it was like in November, I think I was in writing the manuscript at that time, so I didn't explore exactly their reconstruction algorithm, even if we had some exchanges. I think it works a bit differently. In our case, we use a proximal method to reconstruct. So we construct first the speckles, and then we use this reconstructed speckle to get the final image. I think they use more a general way they optimize everything at the same time. I think that's the main difference, but I'm not very familiar with the technique.
Since we're talking about this technique, so you mostly show the illustrations in which you're proportional to IP.
Yes.
Not the square.
Yes. Yes.
So it's possible. Do you foresee any other phenomena, I mean, other than SRS, for instance, in which you could use this linear phenomena, in which you could use this type of...
I think, I mean, we can use definitely this kind of setup for fluorescence. Like it could be used with any fluorescence.
It's like an atom bomb to kill a fly.
And if you wanna do a deep inside tissue, maybe that's a way. But yeah, I guess any incoherent or close to incoherent, or we manage to deal with the coherence of the processes. For example, second harmonic generation. I don't exactly know if it would be possible to use, but we can think.
This one would be square of I.
Yes, but because you have the two, you decouple the two beams. You have one which is focused and the other one which is going to the. So then you can use this. Basically, every second order phenomenon, you can use this technique because you separate the two photons. There will be one photon coming from one side, another one coming from the other side. The problem will be the detection. How do you make sure that it's coming from, the photons are coming from both of the two arms and not two from one arms or two from the other arms? This you need to think, but you can use some modulation in intensity. You can have a look, which we started to think about that. We can use one lock-in, and you have a look at higher harmonic orders. And I did some computation on that, where you compute the harmonics, and there are some harmonics where you can make sure the photons that you're collecting is coming from the two arms, and not two from the same arms and on the other arm. So basically, you can think of any method where you can split in two bits. So at least a square dependency in intensity, even if it's the same wavelength or if it's two different wavelengths.
I was also thinking of absorption contrast, which might be an issue. Here, for instance, you have one of the beams which is modulated.
Yes.
I guess it's quite high power.
Yes.
And you have a lock-in detection.
Yes.
Do you expect that there could be some effects due to heating, changing the refractive index and giving you spurious signals? Or
one thing that we paid attention is in the condenser, so that it has a much higher NA. And also inside there's a nearest that you can close, and we make sure that it was always open, because then you can have this, I don't remember what it's called, but if you're scanning and it's clipping at the detection, it could induce some like fake signal by being modulated at the same rate. Yeah, I don't remember the name of that phenomenon, but yes, we paid attention to that, and otherwise I don't know exactly.
This is just your question.
thermal lensing.
Oh, thermal lensing. Okay, that's exactly why we're also making sure that the objective is there's no clipping in the detection with the modulation. And we run an experiment. I think I put but okay, no, the image that I put was for the water and hot water thing. But we checked that it was not the case.
And staying on the thermal effects, because you mentioned it briefly.
Yes.
So when you spend some time on a broad field of view, I guess you need some. You mentioned that you see some movement effects.
During the illumination, yes, it happens sometimes when the acquisition time is the whole acquisition time is too long. But between each acquisition, I block the two beams and I switch everything up. Like the sample is only illuminated when there's an acquisition. But when there's an acquisition, we're making sure that I mean, if it's too long and it moves, in any case, the reconstruction ends up being quite bad. So, but we don't have any more control of that.
So, I was surprised by a sentence in the manuscript. You said that in SRS there is no absorption, which is absolutely right.
Yes,
but you of course have absorption.
And
from other molecules and.
Yes, but I think this sentence was more meant to compare, for example, with the fluorescence, where we have the quenching.
That's what I say.
Okay.
It's perfectly right, but
okay.
It's kind of twisting the.
Yes. Okay.
Yeah, one thing I'm not sure I understood is the limit of the field of view that you have. So if you just give up the sectioning. Yes. What is the actual limit of that?
Like I don't know how to give numbers, but the main thing is that we work at constant energy for the speckle arm, so the beam which is going to the SLM, and yeah, the energy will decrease as the area of the spread, so it can go down quite quickly, and then the SNR gets worse and worse. And I don't know if it will be it will help, but usually we use 16 to 32 modes on the SM, meaning that in one line we have 32, so 32 by 32 or 16 by 16. And if we go higher, but this depends on the objective and many things, but this is more or less what we were working with. And if we went for higher number of modes, we would not see any signal. So that we would send a speckle, but we were limited by this and not by the other beam which was focused, basically.
And so ultimately, it's the amount of power that you can reasonably send on that.
Yes.
I guess.
Yes, exactly. Okay. Yes, and also like the use of that power, because we don't use spectral focusing or stuff like that.
The very last and quick one, I guess. So you briefly mentioned the speckle decoration, which I guess occurs slower than your imaging time, or I hope so. Is this a
what
problem?
do you mean by
if you have movements in your animal, hopefully one
yes.
day, speckle will decorate.
Okay. Yes. Okay. Okay.
Will that be a problem?
Each image was like it was more on the hertz or higher than 1 hertz, and we didn't really have that issue. Like 1 hertz for biological tissues, it's quite okay, especially if there's no blood secreting, which was like we had the dead samples, so it was not. The only problem, the only moving problem would be the heat, and it's more on the second scale or like a minute scale. Sorry, than a second, I would say.
So I will stop here. And, thank you again for
thank you
for this presentation and your answers to the questions.
Thank you. Thank you. Thanks.
Dario, we send you a Zoom link.
Dario, can you hear me? Dario?
Yes, I'm here. I was muted. Sorry.
Oh, yeah. And Sylvain and Hilton will send you a Zoom link for the deliberations.
Okay. So it's a different room. Okay.
Yeah, it will be a different room. So you can mute here and you will have another link from, or you can disconnect if you want. And you will have another Zoom link with Sylvain and Hilton.
Okay. Okay. Very good.
Thank you.
Thank you.
Nerveux, c'est pas. C'est bien.